Hi, welcome to a new section of this video course, dbus and systemd. In this section we'll start by looking at service support in systemd, and then we'll move on to logging with systemd. After this we'll learn how to use systemd containers and handle device files. At the end we'll explore about dbus communication. Now we move on to the first video of this section that deals with service support in systemd. In this video, we'll start our journey by understanding what unit files are. Then we'll move on to setting the SELinux context for a service and relabeling files during service startup. Lastly, we'll learn to use socket-based activation and governing unit operations. System controlling services such as dbus and systemd are core components of a Linux system, now more than ever. Where dbus offers system and session-wide cross-service communication and process lifecycle management, systemd is a core daemon, offering multiple features. Both services use SELinux to further harden their operations and allow administrators to fine-tune the access controls applicable. Systemd is a core component of many Linux distributions. Since its birth in 2010, systemd has gradually been adopted as the core init system, responsible for handling services and boot-up operations. Throughout its development phase, several other components have been added to the systemd portfolio, which are listed on your screen. The main capability of the system daemon that most people know is its support for system services. Unlike the traditional sysv-compatible init systems, systemd does not use scripts to manage services. Instead, it uses a declarative approach for the various services, documenting the wanted state and configuration parameters, while using its own logic to ensure that the right set of services is started in due time. Systemd uses unit files to declare how a service should behave. These unit files use the INI style syntax, supporting sections and key or value pairs within each file. A service can have multiple unit files that influence the service at large. It's important to remember that different unit files for the same service are all related. Here are the unit files with their definitions and uses listed on your screen. Other unit files exist as well, although those have more in common with generic system configurations, such as slice definitions, paths and auto-mount settings, and less with particular services. When an application is installed on a system, it places its default unit files inside systemd/system directory, from where they're picked up by systemd. At runtime, updates can be placed inside the /systemd/system directory, which will override the unit files in the default location. System administrators can override the configurations by placing unit files in the etc directory. These unit files override settings in run/systemd and user/lib/systemd directory. Now let's take an example and check out the default DNS mask service unit file. So, log up a terminal and type this command, that is cat followed by directory path /dnsmask.service. Enter. This unit file declares the command to use to launch dnsmask and informs systemd that the service should be launched after the network target has been reached, which is kind of a milestone in the boot process, allowing proper dependency handling, and is needed for the multi-user target, which is the equivalent of the default run level when using sysv-style init services. Now let's look into setting the SELinux context for a service. So, when systemd launches a service, it executes the command defined through the exec_start = configuration entry in the service unit file. By default, a standard domain transition will occur as defined through the SELinux policy. When a sysv-style init script is used, the service is launched from within the initrc_t context. With systemd, the context is one from the daemon itself, generally init_t. Not all Linux distributions have an SELinux policy that's already modified to suit the systemd service approach, and might be missing domain transitions from init_t to the various service daemons. Package developers and system administrators can, however, update the service unit files to have the service launched in an explicitly mentioned domain. To accomplish this, the service section of the unit file can be extended with the SELinux context = configuration entry. For instance, to ensure that dnsmask is launched with the dnsmask context, you'd use these lines. Of course, it's also possible to use this to have a service running with a completely different context, which can be useful when developing custom policies for daemons. Some services should only run when SELinux is enabled or disabled. With systemd, this can be defined through its conditional parameters. A service unit file can contain a number of conditions that need to be valid before systemd will consider the service. These conditionals can point to the system type that is virtualized or not, kernel command line parameters, files that do or don't exist, and so on. The one we're interested in is condition security, which is true if the given security system is enabled. For instance, let's look at the rhel auto-relabel.service unit file. So, at your command terminal, run this command and click Enter. This unit file declares three conditionals. The first one is conditional security equal to SELinux. Condition ensures that the service is only launched if SELinux is active. Next, the condition kernel command line equal to auto-relabel condition informs systemd that the kernel command line should be checked. And, if it contains auto-relabel, this service should be triggered. That is, the pipe prefix makes this conditional a trigger. And the last one is the condition path exists equal to auto-relabel condition. Informs systemd that the /.auto-relabel file should be searched, and if it exists, this service should be triggered. Now let's step ahead and look into relabeling files during service startup. Due to its more declarative approach to service management, a number of services are harder to control through systemd than they were using sysv-style service scripts. This is, of course, due to the open and flexible use of scripts to perform any service-specific preparation, which is harder to accomplish with systemd. One of the actions that many services require is the preparation of service-specific runtime directories, such as run httpd for the Apache service. Systemd has resolved this by supporting what it calls tmpfiles.d. These are files and locations that are requested to be provided or updated immediately at boot time, but are not placed in the persisted file system. For instance, the package that provides the Apache daemon installs this definition by default on the system. So when you run this command at your terminal, you'll find this definition as the output. Similar to the systemd unit files, the files that contain these settings should be declared in one of these three locations. Each of these locations overrides the settings of the previous one. The default package provided location is user lib tempfiles.d. Next, runtime declarations can be placed in run/tempfiles.d. And lastly, the local sysadmin provided declarations are placed in etc tempfiles.d. The definitions can go much further than just directory creation. Through the tempfiles.d application, definitions can be set to create files, empty directories up front, create subvolumes, manage special files such as symbolic links or block devices, set extended attributes, and more. One of its features is to set the file mode and ownership and restore the SELinux context on a file Z or recursively against a location Z. This can be used to change contexts on files that have proper context definition in the policy, but whose context is not properly assigned. For instance, Red Hat has this definition active. You could see what I said earlier is clear from this output. It's restored the SELinux context on file Z and recursively against the location Z. The relabeling inside sys is needed because this location will, by default, be labelled with sysfs_t, whereas some of its files are requested to have a different label. The sys/devices/system/cpu/online file, for instance, needs to be labelled with cpu online_t. So let's run another command to make it more clear. Write this command at your terminal and press Enter. This definition ensures that this sudo file is relabeled at boot, so that all other processes that rely on the file being labelled with cpu online_t can happily continue working. The other arguments to the definition are explicitly marked with a dash in the previous example, meaning that there are no other parameters to be set. They can be used to set the mode, UID, GID, age, and argument related to the rule. Now, let's take an example configuration that uses some of these other parameters with the lowercase z or uppercase z state, is the system.conf file. So when you run this command, here's what you get as output. For more information about the definition format, see man-tempfiles.d. Now, how could we use socket-based activation? This is what we're going to see next. The system daemon also supports socket-based activation. When configured, systemd will create the socket on which the daemon usually listens, and will have the daemon launched when the socket is used. This allows systems to be booted quickly, as daemons do not need to be launched immediately. When a client only places information in the socket, the client does not even need to wait for the daemon to be activated. The data is stored in a buffer until the daemon can read it. Only when the buffer is full will the operation block until the daemon has flushed the buffer. So, let's take a look at the systemd-journald socket unit file. For this, you need to execute this command at your terminal. Let's click Enter. Cool. If one of the mentioned sockets, as these which you can see here, is used, then the systemjournald.service unit file is used to launch the service. Inside the socket section, an SELinux specific entry can be defined. For example, an entry like SELinux context from net equal to true. When this entry is set, the MLS/MCS information is obtained from the client context, that is the application connecting to the socket, and appended to the context of the service. Finally, let's look into governing unit operations access. Until now, we've looked at configuration settings related to systemd's SELinux support. But systemd also uses SELinux to control access to services defined through the unit files. When a user wants to perform a particular operation against a unit, such as starting a service or checking the state of a running service, systemd queries the SELinux policy to see whether this operation is allowed. The system daemon uses the service class to validate whether an operation is allowed or not. For instance, to validate whether a user context, that is, user_t, is allowed to view the status of the service associated with the sshd.service unit file, it checks the context of this file, such as sshd_unit_file_t, and then validates if the status permission is granted. So, this is the command to validate and view the status. Let's execute it. In this case, no output is shown, so the user does not have the permission to query this information. Other supported permissions are disable, enable, kill, load, reload, start, and stop. Whenever the SELinux policy denies the operation, it will be shown as this one. In the audit logs, this will be available through a user_avc denial message. What is important to know here is that the SELinux policy contains the access rules related to these service operations, but is not responsible for enforcing the rules. It's systemd that acts based on the policy content, unlike file system operations, which are governed by the Linux kernel and are as such enforced through the kernel as well. In this video, we've learned about service support in systemd. In the next video, we'll learn about logging with systemd.